All right, so lesson 13. And both lesson 13 and lesson 14 are titled Wave Properties. And again, today we're talking about just waves in general. What are waves? And then next week we're going to talk specifically about light in preparation for being able to, explore optics and some other wonderful areas under physics. So here's our first question. What are waves? What are waves? So the simplest way to answer that question is this way, that waves are rhythmic disturbances that carry energy. Waves are rhythmic disturbances that carry energy. Somebody give me an example of a disturbance. I thought for sure somebody was just going to yell out obnoxiously. Right? We all have an idea of what is a disturbance, right? It's something that disturbs you. And the idea here is it's something that disturbs the equilibrium, something that disturbs the medium. And so air, water, those are the media that we interact with most often. But those media have kind of a resting point, and waves disturb those media by moving the particles in those media around. Okay? So that's one thing going on with a wave is you're disturbing the medium. You're disturbing the air, or you're disturbing the water, or even as sound travels through a wall, you're disturbing the wall, that's solid. You're disturbing that medium. And what does rhythmic mean? When you hear rhythm or rhythmic, what do you think of? I know what you think of, Zion. What do you think of? Sound? And specifically, what type of sound is very rhythmic?
A beat.
Yeah, a beat, right? Music. And so with waves, we're talking about something that is very rhythmic. It's regular. This disturbance is not, typically abrupt and then disappears. It's rhythmic. It's cyclic. This disturbance. And then the other part of this, and something that's just as important, is that waves carry energy. So waves are rhythmic disturbances that carry energy. And what is energy again? We talked about this, I don't know, for the first time, maybe back in December. Yeah. The capacity to do work, which means that when we think of these waves as carrying energy, that was weird to tap my head with this. When we think of waves and carrying energy, these waves have the capacity to do work, which makes a lot of sense when you think that light is a wave and has the capacity to do work, right? To warm things up, to facilitate photosynthesis and other phenomena. All right, so waves come in two forms. You can think of it as two forms or two varieties. However you want to think about it is fine. The first kind of waves are mechanical. And mechanical waves require matter in order to transfer energy. That is, the only way they are going to disturb the medium is if there's actually a medium. Like there has to be matter in there for these waves to continue to what you would call propagate, continue to move. And so some examples of mechanical waves. Sound waves, ripples, as you throw a rock into a lake, ocean waves, earthquakes, the wave of people, right? As people are doing the wave at a sporting event. You always have that one person that wants to get the wave going. And so these are mechanical waves. That is, they require matter in order to transfer energy. They require matter in order to transfer energy. The other type of wave, these are called electromagnetic waves. These do not require matter. Now, they'll still pass through a medium, so they can move through where there is matter, but electromagnetic waves do not require matter. in order to propagate. And this is why light can travel through space. In space, a lot of space is empty. It's open. It's devoid of matter. It's a vacuum. And light can travel through that because light is an electromagnetic wave that does not require matter in order to propagate. Okay? And so light is an example of an electromagnetic wave. Okay. So let me ask you this. Can sound travel through the vacuum of space? No, it cannot. Because sound is a mechanical wave that requires matter, which means that you could not actually communicate by sound in space. And that's meaningful. That's meaningful. So if you ever find yourself out in space and you yell to somebody, they are not going to hear you. Okay, sound cannot travel through the vacuum of space. It's also the reason why, you know, we've got this organization called SETI, or this a lot of machinery collectively referred to as SETI, the Search for Extraterrestrial Existence or Extraterrestrial Intelligence, is what it is. And a lot of that has to do with actually broadcasting out messages. But it's broadcasted out as radio waves, which are a type of light wave. And so this happens also when you're talking on the phone. Regardless of the type of phone you're using, it converts sound waves into light waves that then travel much faster than sound waves and have to be reconverted. Okay? Because sound requires matter to move, and it's also way, way slower than light. Way slower than light. All right? Cool? All right. So waves come in two shapes. So they come in two forms, and they also come in two shapes. The first one, these are called transverse waves. And so in a transverse wave, the energy is flowing this way, but the matter is disturbed this way. So in transverse waves, the disturbance, the displacement of the medium happens perpendicular to the way in which the energy is moving. So this is a transverse wave. The materials are displaced perpendicular to the direction that the energy is transferring. Good example of this, ocean waves. Okay, an ocean wave, the water is being disturbed this way as it rises and falls, but the energy is directed towards the shore. Right? That makes sense? Okay, cool. So ocean waves, great example of transverse waves. The other type are called compressional or longitudinal. So this is a transverse wave. Compressional or longitudinal, the energy moves this way, as does the disturbance. So this is a longitudinal wave. Longitudinal wave or a compressional wave. So the materials are displaced or the disturbance is in the same direction as the energy. Anybody know of an example of a transverse or sorry, not a transverse, a longitudinal or a compressional wave? Sound. Sound is probably the best example of a longitudinal or a compressional wave. So the energy moves this way. So as I speak to the people in the back row, the energy is moving from me to you, as is the displacement of the materials in the medium. So remember, sound is a mechanical wave that requires matter. So the only way sound can move from my mouth to the back row is by those vibrations moving the air molecules, moving the medium, displacing it in that direction. And this is why sound doesn't penetrate nearly as far as light does. Because sound requires the medium, that matter, in order to move. And every time it transfers a vibration from one molecule to another, some of that energy is lost, right? That transfer isn't perfect. Whereas light, it doesn't require a medium to transfer, and it can penetrate better than sound does. Penetrate better than sound does. And through some things. There are some mediums that are really good at absorbing light. Like if you use a dark colored wall, really good at absorbing light, but sound will travel through. Right? Sound travels pretty well through solids. All right. Are there any questions about waves? So that first statement is really the best way to address that question. Waves are rhythmic disturbances that carry energy. And I just want you to always think about two things when you think of waves: rhythmic and energy. Okay? Rhythmic and energy. And so yeah, there's a disturbance, but some of our waves, electromagnetic waves, don't require disturbance. They don't have to disturb the medium. They can travel with or without that disturbance. All right? No other thoughts or questions? Or okay. So again, a lot of what we're doing this week, if you weren't here when I made this first announcement, is just kind of laying a foundation of what waves are, and then next week we're going to pick that up and talk specifically about light and do a lot of calculations involving light. And then the week after that, I think actually, rather than talking about springs, we'll talk in even more detail about light, as I think how the schedule is set up. All right, so here is an illustration of both those wave types. So on the board, I just drew you the movement of energy versus the disturbance. But in this, it's actually illustrating the wave itself. And so here we have a transverse wave. And so in a transverse wave, again, the displacement is perpendicular to the direction energy is flowing. And so if this is an ocean wave, you would see this is the rise and the fall of the water as it's moving, as that wave is moving towards the shore. The water actually doesn't move towards the shore until it gets to a point where the depth is less than the height of the wave. Then the water collapses and falls forward. But anyways, it's another story for another time. So in a transverse wave, there are a few things that we're really interested in. We're interested in the wavelength, which is basically the amount of distance it takes to get from one point to the same exact point in the wave. And so it's not from like here to here, we're back at this middle point, but we still have to complete another portion in which you dip below the average point of the wave. So it's a lot easier when you're dealing with wavelength, is to deal with either a crest, which is the high point of the wave, or you deal with a trough, which is the low point of the wave, and the distance from crest to crest, or the distance from trough to trough. And I know in here it only shows one trough, but this wave would continue to propagate further, and we could continue to draw this out, and you would have another trough following a little ways down the line. All right? So that's something we're really concerned with when we think about transverse waves is wavelength. What's the distance from one crest to another, or from one trough to another? We're obviously also concerned with crest and trough, and because of we're concerned with these because we want to know the amplitude, which is the magnitude of displacement. And so especially if you think about the ocean wave as a transverse wave, we're worried about the amplitude because we want to know when is that wave going to crash, and is that energy going to be fully exerted onto the shoreline. Okay? And so we want to know the amplitude. How much is that medium being displaced? And that's what's going on with a transverse wave. By the way, light is also a transverse wave. And remember, light is an electromagnetic wave, so it does not require matter in order to move, in order to propagate. But when it does, it will move through the medium, and it will displace the medium perpendicular to the movement of the energy transfer. Okay. Here's a compressional or a longitudinal wave. And here we're really concerned. You can still talk about wavelength in longitudinal or compressional waves. And what it is it's the distance between one compression and another compression. And so a compression is a point at which your molecules are being kind of forced together. And then a rarefaction is where your molecules are kind of, is basically equivalent to a wavelength. The distance from compression to compression, or the distance from an expansion to an expansion. And so let's look at this in a little bit more detail. Here's, so a rarefaction is where those particles are spread apart. A compression is where those particles are forced together. And so here you can see a compression where these particles are, compressed or smashed together. And in a compressional or a longitudinal wave, the displacement, the particles are moving this way, laterally, in the same direction that energy is moving. And they're either being moved further apart or they're being moved closer together as these vibrations carry from one molecule to the next. And so here's a compression, and then here is a rarefaction where the particles are being spread out. And then so a wavelength is the distance from one compression to another, or the distance from one rarefaction to another. All right? We're going to take a little bit of a moment, and this, again, this day is just a little bit different than a typical day for us, because a typical day for us, we have some problems to solve together. This one, we're laying a foundation. It's very theoretical. And so what I'd like to do is take a little bit of a lecture break at this point, and I would like for you to just take a moment to think about some of the implications of a longitudinal wave moving through a medium, moving through material. What are some of the implications of that? Some of the potential consequences of a longitudinal wave moving through a medium. And I would like for you to do the same with an electromagnetic wave. What are some of the consequences of an electromagnetic wave moving through a medium? Okay? And then think about how would those two consequences be similar, and what would be some of the differences in those consequences. All right? Take about, take about a minute or so. Talk about that with those around you, and then we'll talk about this together, and we'll kind of work through some of these implications. All right? Take about a minute talking with those around you. Come up with some of the potential consequences of a transverse wave moving through a medium and of a compressional or longitudinal wave moving through a medium. All right? And some of those consequences are going to be the same, but some of them will be different. Talk. Forcing some interaction. For some of you, it should be easy. All right, any thoughts? I didn't hear a whole lot of talking and communication going on, so who knows how much, thinking was going on. What are some consequences? Let's just start of just consequences of a wave moving through some medium. And let's make this a little bit interesting. So let's talk about what are some of the just general consequences of any wave moving through, a tabletop like this. Okay? What are some of the consequences of a wave, either type, transverse or longitudinal, moving through this tabletop? What are some of the consequences? What's going to happen? What's this tabletop going to experience? Movement, right? And what kind of movement?
Irregular to its normal.
Okay, so rhythmic, right? Remember we talk about waves being rhythmic. It's going to experience some kind of a rhythmic movement. Okay, it's a disturbance, right? And just because electromagnetic waves, I just said transverse and longitudinal. I didn't say you had to use an electromagnetic. But even with electromagnetic waves, like light hitting this tabletop, it's still going to disturb the medium, even though it does not require matter. Okay, so you're going to see some movement, right? Some movement that is irregular. That is an example of a disturbance. And so what kind of movement happens in solid materials? We talked about this when we talked about heat transfer. You said like in a gas, it's very obvious, right? You heat something up, you increase the kinetic energy, those gas molecules are going to start moving faster. In a solid, it's a little bit different because there's not as much freedom to move. And so what does movement look like in a solid medium like this? What are we talking about?
Molecules vibrating.
Molecules vibrating. And so you can actually feel that. You can actually feel that. As you heat, if you were to heat this tabletop up with a heat lamp, and you were to carefully measure what was going on, you would actually be able to measure the vibrations of the particles inside of the tabletop. So yeah, that is a consequence of a wave moving through a medium, that you're going to detect some movement, some disturbance. What are some other consequences of just waves in general? So it's still going to be movement, but not movement because of disturbance, but movement because of what? What do waves transfer? Energy, right? Waves carry energy. So you're going to also get some additional movement, not just because of the displacement of the wave moving through it, but also because that wave's going to transfer energy to it, right? So you actually get both things going on. You get the displacement, triggering movement, triggering vibration in the molecules, but then you also get energy transfer. And we see this especially with really, really powerful waves, like electromagnetic waves. All right, any other thoughts about some potential consequences? Somebody describe a solid for me. If you were asked to define a solid, how would you do it? So if I just asked you, I don't know, like hypothetically on your homework assignment for this, and then hypothetically next week on your quiz that'll go home along with your homework assignment, and I said, what is a solid? How would you answer it? Yeah, Micah.
An object that can't be like put into a, like you can't like put it into a container.
Okay.
It can't take the shape of its container.
Yeah, good. And so the best way to define a solid is it is a material with a constant shape and a constant volume. Okay? Or what you might think of as a fixed shape and a fixed volume. Because the volume doesn't necessarily have to be constant, right? You've seen this with sidewalks if you heat them up. Like the sunlight will heat them up and then they'll crack because they'll expand and bump up against each other. But a fixed volume and a fixed shape. Okay? So a solid is a material with a fixed volume and a fixed shape. So what's a potential consequence of inducing movement, inducing more vibrations in the particles of a material like that? Cracking it, right? I just mentioned that with the concrete. A potential consequence is to actually break your crystal, break what's forming that solid, to fracture it. Yeah. What's another potential consequence? And think of a solid not necessarily as this tabletop, because you'd have to really input a lot of energy, but maybe a solid like an ice cube. What's a potential consequence of a wave moving through a solid like an ice cube?
It would melt.
Yeah, to melt it, to change its state, right? Another potential consequence of having a wave move through a medium is to actually change its state, to liquefy it, so that it no longer has a fixed shape, still has a fixed volume, but a variable shape. Now it can take on the shape of its container. Does that make sense? Man, usually Wednesdays are a lot more interactive than this. I think it's like waking up and it being 30 degrees outside. It's hard to get used to when you live in Southern California. You know what's really weird? So I lived in Ohio for 4 years, and the winters there are brutally cold. It doesn't snow a lot, but the winters are just brutally cold. Like the average high in January is 18 degrees, is the average high. And so, yeah, like it's fairly regular to get days that it's like -3, -4, and it's really flat there, so it's really windy. It's not completely unusual to get days that are -30 or -40 with the wind chill. You know, it's just brutally cold. And so right now, when it's cold here, and for Southern California standards, it is brutally cold, right? Having a high of 58, right? That's brutally cold. It's 70 degrees in Ohio right now. Like they're having a hot spell at the same time that we're having a cold spell. It's so weird. So like the people we lived with in Ohio are wearing shorts now. And, you know, I actually put on a jacket this morning. I always wear pants to work, but I actually put on a jacket. Just kind of fun. All right, any other thoughts on potential consequences of a wave moving through a medium? Y'all got that? Y'all good? Again, we're just laying a foundation. Laying a foundation here. All right. So I want to show you the electromagnetic spectrum. And this is something we're going to see a lot over the next 3 weeks. And so the electromagnetic spectrum basically illustrates the entire collection of what wavelengths are possible in light. So the electromagnetic spectrum, this is basically showing you the entire spectrum of light. And notice these arrows, okay, demonstrating that there's basically, it probably goes infinitely in either direction. That there are infinite possibilities in terms of expanding your wavelength and shortening your wavelength. But let's look at some of this. Couple of things I want to point out, and again, we're going to talk in more detail about light next week and the following week, but I want to point out a couple of details. The visible portion of the light spectrum, of the electromagnetic spectrum, is a teeny tiny portion of the overall electromagnetic spectrum. A tiny portion. So at least, and this is what we mean by visible to humans, because there are some animals that see wavelengths shorter and longer than what we see, but these are what is visible to humans. And it's only about, 350 nanometers in wavelength to about 700 to 750 nanometers in wavelength. And so nanometers are, 1 nanometer is 1/1,000,000th of a meter. Okay, just to kind of put that in context. And then so this is just a small portion of the overall spectrum. And then look at some of these, like radio waves. Radio waves, the wavelength on this, 10 to the third power. So that would be 1,000 meters. So a wavelength of 1 kilometer. Any of you ever run a 5K? Nobody in here's ever run a 5K? I've run a 5K. I'm in horrible shape. Oh man, you guys ought to get out there and start training. Run some 5Ks. Do some like for charities, right? Help to raise funds. Run like a 5K for the American Heart Association. It's a lot of fun. 3.2 miles, no big deal. But anyways, so 10 to the third power is 1 kilometer. It's a little bit over half a mile. Okay, a little bit over half a mile. All right, and so what you have here is, a wave where you have to go a little bit over half a mile to get from one crest to another crest. And then at the other end of the spectrum, you have a wavelength of 10 to the minus 12. 10 to the minus 12, which is a 0.11 zeros and a 1. Okay? That's really, really small. So just looking at like and that's not even the ends of the spectrum, because they're infinite in either direction. But that's like the end of the spectrum that we know well and can harness and can use to do things with. It's crazy, right? And now light is an electromagnetic wave, meaning it does not require matter in order to move, in order to transfer and move and propagate. And it's a transverse wave in that when it does displace matter, which it will, it displaces it perpendicular to the direction of energy movement. All right? Cool. All right, so let's work through some problems. And again, they're not really math problems. They're just things I want you to do as you practice and continue to work on this foundation. So I'd like for you to take, I don't know, about a minute or so working with those around you, and I'd actually like you to do this. Go ahead and in your notes, draw a transverse wave with a wavelength shorter than the amplitude. So draw a transverse wave that has a wavelength shorter than the amplitude. So the wavelength is actually smaller than the displacement. Okay? Take about a minute. If you want to get some help from those around you, feel free to do so. If you don't want to get help from those around you, feel free to not get help from those around you. It's not real. It's plastic. This one's real, though. It is. All right, so if you're going to draw a transverse wave, you want to draw a wave in which the displacement is perpendicular to the movement of energy. So you're going to want to draw a wave like this, and we want a wavelength shorter than the amplitude. So let's just be really dramatic to fulfill the requirements of this question. So here's our direction of energy movement, and we want the wavelength shorter than the displacement. There we go. So the wavelength is the distance from crest to crest or trough to trough. And that wavelength here is smaller than the displacement, than the amplitude. Okay, so this wave would actually displace matter more than the distance from crest to crest or trough to trough. You okay with this? Obviously a transverse wave because we're noting that the displacement is perpendicular to the movement of the energy, the direction in which energy is being transferred. So this has nothing to do with our class at all, but I put this on and it was disturbing somebody, so I told them that this one's plastic, but this skeleton's actually real right here. But you know, at one point, Pirates of the Caribbean at Disneyland, every skull in there was real. And then over time, they replaced them with molds. And there's only one place in the ride now that actually has an actual human skull. And it's the bed. There's a skull and crossbones on the back of a bed somewhere on the ride. And it's the only point in the ride where you still have an actual human skull. I don't know if the bones are actual human bones, but the skull is. So this is food for thought. All right. So draw a transverse wave with a wavelength twice as long as the amplitude. So draw a transverse wave with a wavelength twice as long as the amplitude. Go ahead and take another minute or so. Draw a transverse wave with a wavelength twice as long as the amplitude. So to satisfy this problem, it might be easier, rather than to measure the distance from crest to crest or trough to trough, to actually just go back to the middle point twice, right? And so that way you can go out and you can mark the top. So that's what I did here. I used the eraser as a guide to give me my amplitude. So that's as high as I want my wave to go, which is right here, which ought to happen halfway in between where I am at the midpoint and where I reach the midpoint again. And then we've got to, oh, sorry, I want to make this really beautiful. Let's get stuck here. And then I marked 2 points here, so I need to be back at the midpoint here, and I need to be back at the midpoint here, and then we'll have a full wavelength. Oh, didn't go low enough. Gosh, I wanted this to be beautiful. There we go. Up. There we go. We have a transverse wave with a wavelength twice as long as the amplitude. So where it's twice the distance to get from crest to another crest as the amount of displacement in the wave. Okay. Pretty straightforward. You'll get a lot of practice drawing waves. You'll love it. You'll be so good at it that by the time we start talking about light, it'll just be second nature. This one should be relatively easy. So draw two transverse waves with different wavelengths. So go ahead and take a little bit of time to draw two transverse waves with different wavelengths. No specification as far as how long the wavelength needs to be. Okay. When I'm given a prompt like this, I like to be as dramatic as possible. So these are transverse waves, meaning the displacement needs to be perpendicular to the movement of energy. And if you want two transverse waves with completely different wavelengths, there you go. You've got two transverse waves with different wavelengths. This one, we couldn't even finish a full wave in the amount of space that we had. And this one, we did a little bit more than a full, almost two full waves in the amount of space that we were given. Okay? Two transverse waves with different wavelengths. What's left for a prompt? What are you searching for? What are you hungry for? All we've drawn so far are transverse waves. What do you want to draw? You want to draw a longitudinal wave, don't you? I do. Go ahead and take a minute. Draw two compressional or two longitudinal waves. Two terms for the same thing. So two compressional or longitudinal waves with different wavelengths. All right, so two compressional or two longitudinal waves with different wavelengths. Again, when I'm given a prompt like this, I like to be dramatic. So again, let's put this on our arrow, signifying the movement of the energy as it propagates in that wave. And then in a longitudinal wave, the matter is displaced in the same direction or on the same plane that your energy moves. Let's get this more compressed. So here we have a compression. Here we have a rarefaction. Here we have another compression. And so the wavelength in this longitudinal wave is our entire energy, our entire line of energy. Okay? And then in this one, we want a different wavelength. And in a longitudinal wave with a really short wavelength, it becomes a little bit more difficult to tell the difference between your compressions and your rarefactions. But we can see we've got a compression here, we've got a compression here, we've got a compression here, and here, and here. And so our wavelength is the distance between one compression and another compression, or one rarefaction and another rarefaction. Okay, and so here are two longitudinal waves, both with the displacement in the same direction as the energy movement, where energy is being carried. And so here, the nice thing about drawing longitudinal waves, it doesn't matter how tall you make these lines. And why is that? Why does it not matter how tall you make these lines? Are we illustrating amplitude here? No, because where is displacement happening? This direction. So it doesn't matter how tall you make these lines because you are not illustrating anything with the height of these lines. You are illustrating everything with the distance between the lines because your displacement is happening this direction. So without the disturbance, all of these molecules should be equally spaced apart because according to what we talked about when we talked about entropy, things like to maximize randomness, right? And when it's most random is when these particles are furthest apart possible, where every particle is occupying as much space as possible. Because that means you get the least amount of interaction possible. Okay, so without the wave traveling through, these particles should all be equally distant. But as the wave passes through, it moves some particles closer together, some particles further apart, as these particles vibrate as the wave propagates through that material. Cool? You gained a love for waves, or at least an understanding of waves. And if this is all like you've done this before in a physical science class, I apologize. But again, we're laying a foundation that we can build on next week as we talk about